Hi. In this unit, we're going to start the discussion of generative adversarial networks, or GANs. This has been a huge industry over the last 5 years, 6 years. And a lot of exciting things have come out of it. And let's start at a fairly theoretical position, understanding. Suppose we want to train a model of the probability distribution over natural images. Now, this has been very effective in language, where you model the probability distribution over English by, training on a huge corpus of raw text. You get GPT-3, the big event of the last few months. Suppose we want to do the same thing with images. We want to train a model of the probability distribution over images, and we would hope that, as in language, this probability model over the space of images would embody some understanding of images. So we could try to use the standard cross-entropy loss, which is how the language models are trained. They've got this nice autoregressive structure that allows us to just use cross-entropy on autoregressive models. But images are structured objects on continuous values. We think of the pixels, the value of the pixels in an image, as a continuous number. And building models of the probability distribution over continuous structured objects is really challenging. A variety of reasons. And when we do variational autoencoders, VAEs will see models that try to take that approach, to try to actually train on a cross-entropy loss. But GANs, very early on, sidestepped this problem. And it sidestepped this problem by representing the probability distribution with a generator. So we're going to build networks that randomly generate images. And if you've got a random process for generating images, that defines a probability distribution over images. And if that random process is seeded with continuous random values, some high dimensional random vector, then we're actually getting a probability density, a continuous probability density over the space of images. Now, if you represent the distribution by a generator, you don't have any way of computing the probability of a given test image. You can generate images, but if I give you an image, you can't say what's the probability that the generator will generate that image. And in GANs, this is overcome by replacing the cross-entropy loss with the discrimination loss. So you have a discriminator that tries to tell the difference between real images, tries to distinguish between real images and generated images. But the first thing I want to do before I write down the GAN adversarial objective, I just want to talk about how we generate random images, what the generator architecture looks like. So this is a picture of an image generator. The image generator starts with a high dimensional random variable, Z. So this is just we're just going to draw a large number of numbers, a high dimensional vector. Each one of those numbers is going to be drawn from a Gaussian, a one-dimensional Gaussian. So this gives us a very high dimensional isotropic Gaussian that we sample from. Then we take that thing and we can resample it, we can reshape it into a 4x4 image of high dimensional vectors. So we can think of our initial random vector as a 4x4 image of high dimensional vectors. And then we do convolutions and we increase spatial dimension down this is called conv transpose in PyTorch, down this conv transpose network until we get an image. And let's go, I've already said that. I've already said this too. We can sample from this distribution simply by sampling this random vector, which is continuous, and then running it through this network. Okay, so how does this how does this network work in more detail? And in particular, how do we define a convolution process that's increasing the spatial dimension rather than shrinking the spatial dimension? We talked about pooling and striding to shrink the spatial dimension when we were building ImageNet classifiers. Here we're taking a random number and we're increasing its spatial dimension. So the first thing we do is we take some low spatial dimension image with a large number of neurons or features at each pixel, and we just apply a regular convolution. This is the same convolution that we saw before, and stride 1. So I can take one of these images, I do a stride 1 convolution, I get an image of the same size. Now, when I do this stride 1 convolution to get an image of the same size, I can use a fairly high a fairly large number of neurons at each pixel. So let's assume that this tensor has a large number of neurons or features at each pixel, at each spatial location. If this tensor has a large number of neurons or features, I can just convert this tensor to one that has twice the spatial dimensions in each dimension, but at each spatial location has a fourth of the neurons. So we take this set of neurons at a given spatial dimension, we take this at a given spatial location, we take this spatial location and we just rearrange the numbers such that we then have each spatial location becomes 4 spatial locations with 1/4 the numbers. And that's represented in this picture by picking a spatial location and blowing it up to be twice as big in space, but a quarter as big in number of neurons. And we just keep doing that. And this will increase the spatial dimension as we go. Okay, what's the abstract formulation of a GAN? So abstraction is fun. Abstraction is clarifying, eliminates a lot of detail. So we've got some space Y. It could be any space, but here we're considering images. And we have a generator. This is the thing that's representing our distribution over Y. This thing that's able to generate images. And then we define this discrimination task. So I'm going to define a probability distribution by flipping a random coin. And if the coin comes out heads, I draw from the population or some test distribution or some training distribution. If the coin comes out tails, I generate an image. Okay, so I flip a coin, I either draw from real images or I generate an image from my image generator. Then I have a label which tells me whether this image was from reality or from the generator. And I ask a discriminator to predict the label. The discriminator has to tell me, is this a real image or is this a generated image? So I can think, now I can, so the discriminator is just solving a classical cross-entropy binary classification problem. It's just saying, when I generate pairs of a label and an image, where this label is going to be 1 if it's from reality and -1 if it's from the generator. And that's what this means. The discriminator simply has to tell which it is, has to predict whether it's right. So this is just a binary classification task. And it's trained by cross-entropy loss. So it's trying to minimize this cross-entropy loss for this given distribution. But now the generator is trying to make the discriminator's job impossible, right? If the generator can manage to exactly match the true distribution, and these two distributions are the same, and the discriminator has no grounds for preferring one or the other, any algorithm for guessing is going to guess, can at best guess at random. So let me say that more explicitly. This is a theorem that can be proved more formally, but it's sort of intuitively obvious that unless the generator exactly matches the distribution, the true population distribution, if it's the case that the discriminator is universally expressive, then it's going to do better than chance. If the distributions are different this can do better than chance. So it is that if we take this objective function and assume that the discriminator is always trained to optimum, then the optimum of this, if we assume universality, universal expressiveness for the generator, is the population, right? So this is a real kind of abuse of the universality assumption, that you can represent anything and that you can eat, and furthermore, training will find it, right? So if both of these can represent anything and training will find it, then the generator will converge on the population distribution. But those are pretty strong assumptions in this case. Okay, we can make the gradient descent algorithm clearer, particularly with respect to the generator, to the gradient on the generator, by writing this cross-entropy objective function for the discriminator as saying, well, half the time I'm going to generate from the population. If I generate from the population, then there's no gradient on the generator. We haven't looked at the generator in this example. So this is half of our objective function is this. The other half of our objective function involves both the discriminator and the generator. So when we generate from the generator, now this half of the objective function has this adversarial nature. And I should have emphasized that back here. These two, I've sort of personified these two parameter vectors, the parameter vector of the generator and the parameter vector of the discriminator. And this adversarial objective is represented by this max-min objective function. So if we look here, when we look at this half of the objective function, we're always updating the discriminator vector in the standard cross-entropy way. We're reducing this cross-entropy loss. But we take the generator gradient in the opposite direction, right? The generator gradient wants to make this loss larger. So the two gradients move in opposite directions. And what happens in practice is that the discriminator tends to win. And the discriminator tends to be able to predict very well. So to give the generator some advantage, you typically do a couple generator gradient updates for every discriminator update, just to give it a little bit more of a chance. And we'll talk about other ways of addressing this issue that the discriminator tends to win. Okay, so this was introduced in 2014. So it's, I keep thinking of the deep revolution as being a recent thing, but the deep revolution is maturing, right? It's 8 years old now. But anyway, this was 2014. What we're looking at here is MNIST. Back then, people would still do MNIST. So we've used the GAN to model the probability distribution over handwritten digits. What we're seeing here is samples from the generator of handwritten digits. And here we're seeing samples. This was also done for faces. Here we're seeing samples from the generator of faces. Now, an immediate objection to GANs is that the generator could, in principle, simply draw images from the training set. And if the generator drew images from the training set, that clearly wouldn't be a model of all images, because the training set's the space of images is enormous, and the training set's a vanishingly small fraction of it. So to test whether the generator has learned to just generate images from the training set, what they've done here is put the nearest neighbor from the training set to this image, right? So we're taking this image and taking its nearest neighbor from the training set, this 9 and taking its nearest neighbor from the training set. And you're supposed to see that this 9 is not the same as that 9, and this face is not the same as that face. It's just sort of a sanity check. But this was 2000. This was a long time ago, and we're going to talk about what's happened with GANs in the next unit. There's this other thing that is worth mentioning, and we'll come back to, and that is it's very difficult to know if the GAN is really, if the generator is really covering the space of all images, it could be leaving out some, big pieces of that space. Sampling from the training set is an example where it's leaving out big pieces of the image space. But it could be leaving out big pieces of that space, but still making the discriminator's job really hard, because the discriminator would have to sort of recognize where and when things are being left out. And the bottom line is there's no good quantitative performance measure on how well the GAN has trained the generator to model the distribution. There's nothing like the cross-entropy loss. In language modeling, you can directly measure perplexity or bits per character and get a measure of some measure of how well the model is modeling the data. That's much more difficult with GANs. So there's this thing called the FID score that tends to be used, the French Inception score. So what's going on here is you take the Inception network. So you may remember that the Inception network was this incredibly complicated but very deep network that came out of Google for ImageNet classification. But they just picked this for no good reason. They picked this particular network and they picked a layer in this network. And that layer in the network assigns a feature vector to every pixel in the image, or maybe some downsampled image. So what you do is you take real images and you look at the features that are computed in this layer of Inception. And you take the generator images and you look at the features that are computed in this layer of Inception. And then you take statistics on those features. You take the statistics on those features in the real images, and you take statistics on those features in the generated images. And you see if those statistics match. If it's the same distribution, the statistics have to match. And that gives you a kind of a distance, this distance, the French Inception distance, FID, between the real images and the generated images. And this has been used throughout the history of GANs as a surrogate. People love bake-offs. You love to say, my number is better than your number, I'm on the top of the leaderboard. And so this is what has been used quantitatively. Okay, in the next unit, we're gonna see what's happened since 2014. Thanks.